Hello, everyone. Howdy, howdy. So, couple logistics things. Obviously, the free response grades are out. I posted those. There was not a curve, but what I did with the grades, so just so y'all know, the grade is outsourced to other people. Why? It's a lot of grading. Now, what I do to make sure that the grading is accurate to how I would like it to be is I grade a subset of them. I grade like a representative sample, about 20, 30, something like that, around 30, almost 10% or so. Might be a bit more in this next test. And then I use that to kind of calibrate the grades from the graders. So that's how the grading is done. Now, to that end, I graded pretty generously, specifically on the lower end. On the lower end, pretty generous in giving points where things. So anywho, so that's kind of a thing in there. And then I use that to calibrate. So on the lower end, grades were adjusted. There were some points given in a pretty generous way on the lower end of the responses. On the upper end, they were fairly accurate. And a reminder to you all, just to keep this in mind for future things, remember that you basically get like a point or two. You get between, I think, it's either 2 to 3 points, something like that, from having a picture and identifying the variable you're solving for. That automatically gives you a few points. What then gives you another few points? Identifying the appropriate equation that you're going to use. If you do those two things, you are basically at 50% of that problem with no extra work done around that. As long as you identify the correct formula to use. Because if you do that, then that means and then execution is kind of the last 50%. So it's not terrible to get in my opinion, it's not too hard to get the 50% on the free response. But the reason is you got to know how to do the problem. You got to be able to look at it and say, hey, here's what I'm solving for. And pro tip, the equation you're going to use to solve it will have that variable in it. Guaranteed. You will need to have an equation that has that variable in it at some point. So, anywho. I think I have landed, and again, not finalized, I'm pretty confident in this, that what I'm going to do for test 2 is 15 multiple choice like we did, but instead of the 3 free response, each with 2 parts, so that was 6 questions total, you kind of take quote unquote 4 of them. I'm going to give 4 separate problems and pick 3. So 4 problems, pick 3, they'll all be independent of each other. There won't be any part A or part B. And the benefit here is something I didn't even think about, is that when I gave you 6 questions, I'd actually like read through all of them to identify the ones you wanted to solve. So by reducing it from 4 to 6 to 4, that'll reduce some of the time there. By making them independent, it gives you a bit more kind of flexibility. And then by reducing it from you solving 4 problems to 3 problems, that hopefully gives you a little bit more time to kind of check your work and things like that. Generally, what I saw on the tests when I looked through the free response, either people kind of had a sense of how to do it, or not at all. Time didn't seem to necessarily factor into how much people wrote down. It was generally either they had the right process or they didn't know the variable to solve for, the wrong technique, or whatever. All right, great. There's that. On the topic of grades, I sent out an announcement because I get a couple emails about this here and there. So remember, there's a couple things I do to the grade that can't be done in web courses. Specifically, I will calculate your grade at the end of the semester with and without the iClickers, and I will take the higher of the 2. This is beneficial for people that didn't sign up for iClickers at the beginning of the semester, or just didn't attend class the entire time, but still did well on the tests. So the way that works is if the iClickers aren't included in the final grade, everything fills the hole. That's kind of left behind. So anyway, that's one thing. The other is that your final can replace your lowest test grade. The final is all multiple choice, which means you're like, oh great, this would be easier. It would be kind of a conglomerate. It will have more difficult multiple choice in it to account for not having the free response. It will still have the idea of the same depth and breadth. The final is cumulative. The final tends to kind of average between test 1 and test 2 in my past. But I will say that the final tends to, like, it's the entire course. Cumulative finals are a lot, and I recognize that. So, anywho, it's a thing that exists, that idea that final replaces the lowest test grade and it's higher. But after as you get closer to test 2, you should have a pretty good sense if you think that's something to bank on or not. Yeah.
On the final, do we get the note card?
Yep, you get the note card. You all are still blessed with the note card. In future semesters, we might have a common final across the course, in which case that won't be the case. But yes, you won't get a 5x8 note card on the final as well. Alright, so I made a little spreadsheet here that you all can kind of download. I'm just going to use the example one. I don't know if it really matters. I'll use the example one so I have to type things in. So the way it works, I'm going to open both of them. This one's going to prompt you to make a copy so that you don't edit the original document. And so the way this spreadsheet is designed is it has all the assignments up here. All the red boxes are the ones that you fill in. So for example, say in discussions, now discussions is the one hybrid score. This includes your attendance and your completion on the assignments. I might update that to make it a little easier, but for now it includes both. So let's pretend you got a 90% on the discussion. So you type 90% here. Notice the red goes away. Say in iClickers you got a, let's go 70%, just to make it lower. Quizzes, you got an 80%. The AI proficiency assignments, which I'm going to talk about right after this. Let's say you did all of those, easy 100. Let's say the first test didn't go so well, you got a 50. Second test, you got a 70. Great. You fill all that in, and it shows you your current grade in the class with iClickers, without iClickers, and without the final. If you want to account for the final, so right now this shows your final grade in the class. It's very low. Why? Because the final, i.e. the final exam hasn't been put in. So say you get a 60 on the final. It then shows you your grade in the course with and without. Letter grade, all that kind of jazz. And what you can see down here, I know it's a little small, is that 50 from test 1 gets replaced with the 60 on the bottom. Okay, so it does kind of all those things that web courses can through the power of math. So this exists, use it. Something I haven't looked at, I forget when it is. Let's look it up real quick together. This is something that is always relevant for everyone to kind of consider, is the withdrawal deadline. Not because I want everyone to withdraw, but because it's something that is an option. So the withdrawal deadline is unfortunately before our second exam. Just how it kind of panned out. So you won't have the test 2 exam scores by then. Withdrawal deadline is October 31st, and before that date, you need to make an honest kind of evaluation of can you achieve what you want to achieve in this course? Can you get to where you want to get? And how to do that, you can kind of look at test 1. You can kind of almost like retake test 1 if you wanted to. That can be a proxy for some measures. You can do all the quizzes. All the quizzes up to that point you can do, and basically pretend like it's a mock exam. You took all the quiz questions, you kind of slammed them together. That would be effective. It'd be kind of sort of like a test 2, without using any resources. And yeah, if by that point that goes really poorly for you, that might be an option, because the test will be the following week. In 1 week, you can only get so much done in 1 week. So anyway, that exists. Be mindful of that. All right. Last logistics thing is I have posted the first AI assignment. This is a very straightforward, this should not take you much time. In fact, this is something you're probably already doing. It's me just getting the responses from you all. Or if you're not doing whatever. Remember I told you all, large language models, whether you like it or not, they exist. And it is an important skill to be able to utilize them effectively. And effectively meaning that you work with them, not that they do all the work for you. If they're doing all the work for you, then why are they paying you? That's basically the question here. If you are not playing a significant role in the use of applying these, then AI can take your job. That's kind of it. You need to be able to use them to generate more value than it can generate by itself. How do you do that? One, you become an expert in your subject. You become someone like AI only knows to answer the questions that it can think about. It can't think about certain questions unless you prompt it. That's where the human still comes in. But to that end, I made this guide. I talked about it last class. There's a PDF of it. There's a Word document of it. And the analogy I gave you all is, I've mentioned this several times, driving a car. There's various levels of driving a car. You can watch someone drive a car, that's passive. You've done almost nothing there. You watch someone else do it and said, that makes sense. And that can be useful. They can be useful to watch someone else do something. There is value in that. There is value in learning and seeing, oh, this is where the gear shifter is. This is where the steering wheel is. This is which pedal the brake is. It's like, there's factual pieces of information that first level is useful for. But it is exactly what I said, it's passive. You're not engaging your brain that much. The next level, maybe you're kind of looking it over and thinking a little bit. Maybe you're engaging with it a bit more and thinking about what would happen, but it's still fairly surface level. So maybe you're now in the car. You can see things a bit better. You're evaluating what they're doing in a higher detail. You get more information, but at the end of the day, it's still doing the work. I want you all in the third level, and this is what I want to prepare you all for, and that's the purpose of this assignment. How do you use it as a learner? How do you actively engage with it? How do you make it so that you are the one actually doing the work, but you're utilizing it to assist you? So think of all the things in your car, lane assist, cruise control, things like that. They're great, but I am not going to trust those things entirely. I'm going to be engaging with this. Your hands better be on that steering wheel when you're on the highway. Please, don't trust it completely. Be engaged, be active. This is the learning kind of stage, where it is doing some things to help you, but you are still doing the work. You have a pencil in your hand or a marker in your hand, and you are writing, and you are engaging in doing. Now, how do you do so? I have a bunch of tips here, some prompts to kind of ask it, hey, I did some work, give me some guidance, or hey, I'm stuck, got to this point, help me through it, or use guided inquiry where it's asking you questions and it's not just spitting out the whole answer. In these, you are giving it the problem, but you're giving it, hey, work with me, don't do everything for me. Make sure you give it a clear prompt. Ask follow-up questions. Why did you do that? What if I did this instead? What if the problem was solving for this variable instead of this variable? What might that look like? What if, so on and so forth. And then make sure the answer is correct. I provide the answers, so that gives you an indication that they're correct. But this is a very, very important skill. I mentioned this a few times. AI is about as correct. Currently, when I use it for physics problems, it is correct about as much as I am. Pretty good, but still makes mistakes. So, what is the assignment? Super, super easy assignment. It's just graded on whether you do it. What initial prompt did you give it? Maybe that was the question. Maybe that was the question with a follow-up. Maybe that was, hey, here's my work. Give me some pointers on it. And then the whole point of this is that you have 3 follow-up questions. It's a conversation. When you engage with AI, they call them conversations for a reason. If you are just putting stuff into enter and then spitting out a bunch of things, you're using it like a Google search engine, there is value in that. But learning to engage with it, like you would a tutor, is valuable. And so you put what's your first follow-up question, second follow-up question, third follow-up question, and then, just a quick reflection. Did you find it useful? And then you just copy and paste the entire log. Fairly straightforward, fairly quick and easy. It's a lot of this copy, but this is helping you, give you an assignment to actually practice using this. You can use any LLM you want. Rule of thumb, if you have one that's paid for it, use that one because it's going to be better than any free one. Otherwise, take your favorite.
Do we have to ask it a physics thing, or can we ask it?
Oh, that's a good question. I honestly, you could ask it some question. Okay, so I did say physics problem. It needs to be some STEM problem. I actually don't really care if it's physics, but it needs to be some problem solving. So here it does say physics, but I'm honestly cool with using it to help solve any kind of problem that has multiple steps in the process. I recently used this to try to fix my refrigerator. It was not successful. It did identify the thing, but then I made a mistake at the end, and my fridge is dead. It's very sad for me. Pro tip, make sure all your cables are plugged in. My ground was not connected to a panel, and I think it fried things when I plugged it in. Be careful with your grounds and stuff like that. Anyway, Any questions about the spreadsheet, about tests, about the AI thing, about the logistics?
On the bottom question, which is like, show me the whole thing, do you like?
Just copy, paste it, shove it in there. Yeah, really straightforward. Just put the whole thing there. It's just so I have that data kind of thing. So obviously don't put anything confidential in here that you don't want to share. I don't know why you would. And a question about physics, but yeah. When is this due? Thank you. This is due, I believe, in a couple weeks. Let me confirm that for you. The 27th? 25th? Yeah, I think it's next Saturday. So you'll have 2 weeks to engage with this. The reason I made this assignment is you all should be practicing the problems currently. This is used for learning. When I say that, make sure you all are doing the problem sets in a way that is active learning. If you're only using the quizzes to learn, it is not enough for most of you. Some of you, the quiz problems will be enough, but that's maybe 20% of you. People pick things up at different speeds. Most of you all have to spend the time on practice. It's how it goes. It'd be really cool if everyone learned things super quickly and super easily, but that's just not how life is. Some people gain muscle mass quicker in the gym than other people. That's just how people are different. You're good at some things, you're bad at some things. I could not possibly tell you what you're good at or bad at because it's too unique to you. But be okay with it being a struggle. If everything in life is easy, then you're not pushing yourself. You're probably not achieving your potential. That is kind of the rough reality. If this is easy, then you have you can do more in some way, in some area. Anyway. All right. We're going to go ahead and finish up last classes. There's a problem I didn't get to. And then we'll start the new stuff. So there was one problem I wanted to get to from last week. I did do a live stream of the class we missed, so it exists in YouTube as long as YouTube exists. So Tuesday's class from last week, the one I was sick for, I did record it. Okay, am I in the right folder? This is Studio, that's why. All right. I was confused why this one was complete. They actually got through everything. So we're going to do one last problem, a couple clicker questions tacked at the end. I'm going to kind of go through this a little quick for the sake of time. So last class, we talked about force in a moving wire. We practiced right-hand rule. We did a couple of problems with it. It was a great time, so much fun. We then talked about what if your wire there's two scenarios. What if your wire is not straight or your magnetic field is not uniform and it varies in space. So we did one of those cases, a non-uniform field. We built the integral and it was a pretty easy, there's the problem. It fits in a very small amount of space. There were steps and there were decisions you had to make. But really, it's not too bad. All right. Here's another problem. This is the other problem we're going to work on. Then we got a couple clickers and then we'll jump to the next PowerPoint. In the image below, I have a half turn of wire along with two straight wires. And part A says find the force on the half loop of wire. Find the force in the two horizontal pieces of wire and find the net force. The reason it's broken into pieces is if we find the force on each piece, we can just add them together, assuming the forces are parallel/anti-parallel. So, let's look at this half loop here. Now, the key to the half loop, anytime you all do these problems, the first step you should do, again, every step I'm going to be saying is this step here, is this process here. First step, draw a picture. Pick a couple pieces of wire to find the direction of force. Then we write the integral. So, okay, first we identify we're solving for force. F equals question mark.
How do you know this is an integral?
It's a good question. So the first step here is when to use the integral. Use it if the wire is not straight or if the magnetic field is not uniform.
So like for part B,
No, correct. For part B, we will not integrate. All right, so let's go ahead and pick a couple pieces of wire. So I'm going to pick this little piece of wire here. I'm going to pick this little piece of wire here. And I need to draw the directions of current. To do right-hand rule, I need to know the direction of those arrows. So you can see here my current is making a counterclockwise loop. So this arrow here, let's call that like DL1. And let's call this one over here DL2. DL1 points down to the right, DL2 points up to the right because tangent to the circle. Then you do right-hand rule. We point our fingers in the direction of the current, which is down to the right. And I want to swing those towards the magnetic field. My magnetic field is an X, that's into the page. I want to swing my fingers to be able to point into the page. And when I do so, I get a force that's up to the right. So my force on this wire, if we use a green, is going to be up to the right. Remember, this force is always perpendicular to the direction you're moving and the field. That's the rule. That's why we do this whole right-hand rule. So we're going to call that DF1. It's not the entire force. It's a little piece of the force on the little piece of the wire. You then do the same process on the other side. Fingers in the direction of the current. Make it so you can swing up inwards. Imagine that vector is getting swung inwards. When I do so, you find a force that is up to the left. We chose these pieces of wire on purpose such that you can see there's some symmetry here.
Is the force always drawn from the tail?
Yes, that's a great question. Whenever we draw these vectors, we do draw them starting at the tail. Yes, that is a great question. When you draw that's just kind of convention. It's convenient that way. Technically, this wire is infinitely thin, so it's like there is no length to it, but yeah. That's usually just handy to keep track of vectors, is draw their tails together. All right, through the power of symmetry, you can hopefully see that the x and y, the x components are going to cancel. One's pointed to the right, one's pointed to the left. Symmetry, they're going to cancel out the x components, so we're only going to care about the y component. That's a good thing to have somewhere in your brain. Now, we can also see that we got an infinite amount of these little pieces of wire, so this is how we know we're going to do an integral. We need to find the force acting on all these little bits of wire, and so remember that's going to be I times the magnitude of dl times the magnitude of b times sine of the angle between them. We write the integral. Yeah?
So I have one quick question.
Sure.
With the force vectors you drew, did you need to make them different sides?
They should ideally be the same size, and it would have been a bit better if I'd drawn this one. In fact, I'm just going to move it so it's a little bit easier to see when people look at this later. If I'd drawn this a little bit more up, and I'd done a better job of drawing this vector kind of perpendicular, they should be the same size and symmetrical about the x. Yeah. That is a good point. The better you draw your picture, the easier it is to see these things. All right, so that's my integral. Awesome. Just to make sure I'm following the steps I told you, great. Next step is to write dl in terms of the some spatial coordinate. So if it was a purely left, right, or up, down, you'd use dx or dy or dz. If we have a curved piece, we do arc length. So we do r d theta. So we're now going to write this as integral of I times r d theta. It's a little r here because that's the radius of the wire. We are trying to find, the radius of the wire here. Magnetic field is still magnetic field. That's great. And sine of theta. And I'm also now going to point out, we can do this now. This theta is the angle between my current and the magnetic field. My magnetic field is pointed into the page. Therefore, any arrow I draw on this page is perpendicular to it. So this might take some thinking for you to kind of see this. It's a little tricky for me to draw this. In this picture, the angle is always 90. Because the magnetic field is into the page everywhere on it. No matter what DL I draw, it's going to be 90 degrees to it. That's something you might have to think through or visualize, draw out yourself to understand that.
Can you explain one more time how you got the second and third one?
Oh, I just replaced DL with RD theta. Yep.
Is the green arrow going into?
The green arrows are pointed kind of towards the middle. They're pointed directly towards the middle. Yep. All right. So we have this. Now we need to break it into components. X and Y components. We cannot just do this integral as is. Why? Because currently this integral is adding up vectors that are not parallel, that are not anti-parallel. One's up to the right, one's up to the left. You cannot just add them. Now, we are fortunate that the x component is 0. How do I know that? From the picture, from symmetry. The y component, we are going to do I times r d theta times b, and we're going to do the same thing we've been doing, and it's very convenient for us. So if we look at this vector here, I'm going to zoom in a bunch. I'm actually going to like expand this arrow. I'm going to exaggerate the arrow because otherwise it's going to be really hard for me to draw this there. I just don't have space. To break it into its y component, I need that angle right there. All right, so there's the theta. Now something very convenient is the theta that we're integrating d theta. What are we integrating from? When the line is like this, all the way we kind of arc that line along it until we get to the other side. Why is that convenient? It turns out that this angle and this angle are the exact same thing. Opposite interior angle, it's not opposite interior, it's parallel line theorem or something like that. I always forget the names. Anywho, what it ends up being is what you want it to be. It ends up being sine of theta, and it's actually the same theta that we're integrating over. That might take some thinking to see that, but we're integrating over this length of a wire, so we start on this left side, and then we kind of move around it, and so we're sweeping an arm around the thing. We're sweeping this arm about it so that we start at this kind of purple line, and we sweep that purple line throughout the whole circle so that we add up all the pieces.
Is that always true for all these?
Yeah, it ends up being this way for all these ones. Yeah, the angle is the same. And this is a super easy integral. The only thing that we need is the bounds. I'll give you all 20 seconds to think about those bounds. All right, and the bounds are going to be 0 to pi. We start with our arm that's kind of here, and when this arm is like this, the angle is 0. And then as we sweep that arm, we reach all the way to the angle b pi. Very easy integral. I is a constant, r is a constant, b is a constant. Integral of sine theta, it's just negative cosine theta. Yeah?
Why don't you do pi to 2 pi?
Why don't we do pi to 2 pi? That's a good question. Because our arc starts like this, and our angle is this angle. It's how our angles are defined. And so our angle here is defined when that angle is 0. Yeah, that's why. I suppose you could sweep, yeah, it's just how the angle is defined. And that's why it's important to have it in your picture. So I times r times b times negative cosine theta evaluated from 0 to pi. Cosine of pi is negative 1. Cosine of 0 is 1. You end up spitting out just a 2. There you go. That's the integral. That's the force of the magnetic field on the arc here. Yeah. Oh, the direction of it is going to be up. We get a positive answer. And we can see here all our forces. Thank you for adding that. Up. Yeah, great question. The question was, if my original sign here was not 90 degrees, what would I do? Say, for example, this magnetic field wasn't perfectly into the page. Maybe it was like up at an angle. 1, that'd be very hard for me to draw, which is kind of annoying. 2, the angle would be a constant, so you just put out whatever that angle is, and sine of that angle would be a constant everywhere on the wire. Oh, yeah. So this theta is the angle between B and DL. So I'll write that here. 90 degrees between B and DL everywhere. Everywhere. Yeah.
Sorry.
No, sorry. Remember later. All right. So that's that one. I'm not going to do the straight lines. The straight lines are really straightforward. It's just ILB. So the straight wires, that's a good exercise for you. They're really easy. They're just I times L times B. Super easy. Yeah. Sure. They're different. So these thetas represent different things. This theta down here represents the angle between where I'm at and kind of this horizontal line. And that's the angle we're integrating over, whereas the other angle is the angle between the field and the current. All right, we'll do one more. Oh, did you have another question as well? All right, one more question, then I'll keep moving.
So it's probably a stupid question, but we always assume that like on these kind of problems, like we're doing this as a whole positive charge.
Oh yeah. You're always great question. Are we always assuming that this is a positive charge? Yes. How is current defined? Current is defined as the flow of positive charges. Always. That's a great. Current will always be right-hand rule. Yep. All right. Now that I've solved this, I am going to show you all a trick. I'm not going to put it in writing because I don't want people to get too confused by it. So you all are going to do the sides of the rod on your own. Just for the sake of time, I don't have time to do it, but they're really straightforward. We already did examples of it. I want to show you all a trick. That's going to be kind of interesting. Again, this is not one I'm going to have in writing because I don't have the time to flesh it out completely, so if it doesn't make sense, just ignore it. If you all have an arc, so there is a rule, actually, we're going to come back to this in a couple slides. The trick, I need you all to understand, these next couple slides are going to help us understand the trick. All right, I got a loop. What is the direction of the force on the bottom of the loop? So I've got a magnetic field to the right, and I've got a loop of wire, a square loop of wire, and I'm asking for the force just on the bottom side. Is it into the page, down, 0 Tesla, or to the left? I'll put the unit there so it's correct. Yeah. The unit for magnetic field. All right, give y'all 20 more seconds for this. All right, in 5, 4, 3, 2, 1. All right, so my magnetic field is to the right. My current is also to the right. So if we try to use right-hand rule, we run into a problem. Remember right-hand rule, I want to swing it in the direction of it. It's already pointed towards it. So that's kind of a problem. And so then how do we resolve this problem? We remember the equation is I times the magnitude of L times the magnitude of B times sine of theta. And when they line up with each other, that angle is 0, and therefore the force is 0. When they're parallel, there is no force. When you're moving in the direction of the field, there is no force. So that's actually something you just kind of have to know before doing right-hand rule. Remember this, right-hand rule is for the parts that are perpendicular. All right. Next one. What is the force on the right side of the loop? So same loop, but now I'm asking about the right side of the loop. Is the force into the page, out of the page, 0 Tesla, or left? Yeah, ignore it for now. Yeah, we're just looking at one side at a time. We'll use symmetry to get the other sides. So we're not going to do every single side today, but by doing 2 of them, we can guess what the other side is. Yeah, you pretend like the rest of it doesn't exist. If I say find the force on this right side, you only focus on the right side. If you want the force on the whole thing, then you find the force on each side and you add All right, 15 more seconds. All right, in 5, 4, 3, 2, 1. All right, so on the right side, I put my fingers up, and I want to swing them. I want to swing them in the direction of B. Something that's helpful is to draw the B next to the current, because then we can see that I need to swing it kind of to the right. So I put my fingers up, I swing them to the right, and my thumb is into the page. So my force on the right side is into the page. Now, I'm going to go ahead and complete all the pieces. On the bottom, the force is 0. On the top, the force is 0. On the right, it is into the page. There's my notation for into the page, that X. On the other side, the current's the other way, so it's going to be the opposite. So we end up with something interesting here. The force on the bottom is 0. The force on the top is 0. The force on the right is into the page. The force on the left is out of the page. If you added up all those forces, you get 0. You get a net force of 0. Now, that does match what I taught you all before. Remember, I taught you all before that magnetic fields cannot do work. They cannot make things go faster or slower. So this entire object, even though a piece of it, this right side will start to speed up, the left side's increasing its the entire object is not, its tangential location is not changing. Now, what is it doing? It's spinning. This thing will spin in place. In fact, it'll spin and then at some point it'll actually stop. It'll spin. And if you think very cleverly about this, anytime you all discover something like this, where if I do this, something starts moving, what is a device that makes things move? A motor. This is how electric, well, the magnets are used in these. This is how electric motors work. Every single electric motor uses this principle to go from electricity to motion. A hand mixer at home, electric skateboards, electric cars, literally a blender. Literally any appliance that you plug that uses electricity to make motion is using this. That's how it makes the motion. It has magnets. Most of them have magnets, except some that don't. They use the same principle. And you got current carrying wire. And by applying a magnetic field to a current carrying wire, you make a force. By making a force, you can make motion. Specifically, a spinning motion. You can convert a spinning motion into a translational motion. There's like something called a Scotch yoke, which is a specific kind of motor that takes rotational and makes it linear. But yeah, once you get something spinning, you can make any kind of motion you want with it.
Is that how like CT scans work too? Like when they spin around?
Any electric motor that makes things move is using this principle. If electricity is making it spin, it's using this. You now understand the basis of electric motors, which 95% of people have no clue. They're just like, I put electricity in and it spins. This is it. This, what I just taught you, is all you need to know. Now, you do need to make like the current flip directions. So there's like there's brushless motors, there's brush motors, there's this thing called a commutator. And you all can look into that more on your own if you want to. But you got to keep either like flipping the direction of the current or flipping the direction of the field to keep it spinning. Otherwise, it'll do like a half turn and then stop. And you can go through the exercise of why it would stop. But great, electric motors. You have the basis for it. That's it. That's all that's going on physics-wise. Now, back to the shortcut. The net force on any loop of wire is 0. That is always true. If you have a magnetic field acting on a loop of wire, the net force is 0. It's a closed loop. That is a fact. How is this useful? If we go back to this problem here, the little trick is we have a half loop here. What if I just pretended like it was a full loop? So what if I just pretended it was a loop of wire like this, a half loop? Fun fact, the force on the top of that loop is exactly equal to the force on the bottom of that loop. They have to be. If the net force is 0, then the force on the top has to equal the force on the bottom. So we found that the force on this top of the loop was equal to I times B times 2R. Well, how big is this wire on the top? The length of this wire on the top is 2R. It's 2 of the radius. So what's the force on this top of the wire? It's going to be I times L times B sine theta. It's just a straight wire. What's my I? What's my length? 2r. What's my field? It's B. What's my angle? Oh, it's the exact same force, but opposite. So this is actually a little trick to solving these. If you ever have some crazy looking wire, if you just pretend like you make it into a loop, the force in that straight piece that you make is exactly equal and opposite to the one that the crazy side. Even if that crazy side was like something like this, if I just connect a straight wire, I can find the force in the straight wire and flip it. It's a nice little trick. Yeah.
How'd you know it was 2R?
Yeah, it's a circle with a radius of r. So this side is r, this side is r. Yeah. All right, great.
So the force will be the same even though the length.
The force is the same, yeah, because what's happening here is my angle is constantly changing. Here my angle is a constant, and it just, because that rule and the force on a closed loop is 0, it's a nice little trick. Yeah?
You say full loop, how come you don't need draw the other half of the circle?
Don't have to. A loop is just a loop does not mean circle. That's a good thing to keep in mind. We have in our mind, we think like hula hoops and they're circles. A hoop doesn't need to be a circle. A hoop is just a closed path from one end to the other. Anytime we use the word loop, it just means a closed path. It can be a crazy looking path, but it's closed. That's what matters.
You said it was 2 earlier because it was the interval was from 0 to pi.
Yep.
Isn't the interval from the entire thing be 0 to 2 pi or?
So in this case, we don't need to integrate. On the top is just a straight wire. Straight wires are great. It's just ILB. All right, one more, and then we'll move on to the next PowerPoint. Yeah.
On the test, do we have to write out the integral?
If you know this trick, you can use the trick. Yep. But the requirement of this trick is that you realize that the force is 0, and it requires more conceptual understanding. The integration is just kind of math. This requires you to conceptually understand how to do this, that the force is 0. And honestly, on a test, these kind of ones are good. I'm more likely on a test with these half loops, I'd probably ask you the direction of the force if I ask you a question. If I'm going to ask you a free response problem, I'm probably going to force the integral by making you, in the field, non-uniform. So, just so it's not a super trivial answer. Generally, the free response, I do want you to work things out. The work's not anything crazy or long or complicated, or I say complicated. It's usually not long, but I generally do want you to kind of work something out. So yeah, this is more likely to be a free response, the straight wire. And that's even on the quiz, I put a straight wire as well for that reason. But I could put the half loop as a multiple choice and say, what's the direction of the force? And that's going to test, can you do a bunch of pieces together?
I just don't know where to start when it comes to the half loop question. How do you even formulate to start out with green arrows, it's DF, DL,
There's a step-by-step up here, and I just follow that. One of these PowerPoints, it's saving right now, so I can't open it. Yeah, so I just did that step. I did exactly what it said. I drew the tiny 2 pieces. I found the force on each piece. I wrote the integral. I replaced dl with dx.
We just assume it all goes into the middle.
No, you got to actually do right-hand rule. You got to do fingers in the direction of current, swing it towards the field. Yep. All right. So, on to this one. I fully expect this PowerPoint to roll into next week a bit. That's fine. We're doing pretty decent on time. At risk is some of the AC circuits. So, for test 2, it's DC circuits. That 1 week we did. It's everything to do with magnetism. And then hopefully we can use some AC circuits just a little bit. I plan on being able to cover everything we need in AC circuits in a single class. Not by cramming it in there, it's just not that much that we need to get through. And then hopefully that leaves optics, but if we don't get through AC circuits, it'll just get bumped afterwards. As long as I get at least a week of optics, that's, I guess, okay. All right. Sources of magnetic fields. So we have talked about forces due to magnetic fields. Now we're going to talk about sources of magnetic field. This is the exact same process we did with charges. We talked about forces on charges, and then we said, what's causing those forces? Fields. How do you make those fields? And that's actually the exact argument path we're going to use for this one as well. So you need to remember our vectors, cross product, current is defined as the direction positive charge is moving. Magnetic fields for, the stuff we've been covering. Nothing crazy. But we're going to use it all. All right, we got quite a few things here. Again, I don't plan on, we'll probably go into next week a bit, specifically Ampere's law. We're going to find how to get the magnetic field due to a current carrying wire. And there's going to be specifically two geometries we're going to look at. We're going to look at a straight wire, and we're going to look at actually I guess three geometries. A straight wire, an arc of wire / an entire loop. It could be an arc or a loop, depending on how much it is. And then we'll look at solenoids. So yeah, center of loop, straight wire, and then we'll do Ampere's law, which is going to be like Gauss's law. Yeah, which might get some I didn't like that. Here's the way to think about this. You've at least practiced some of Gauss's law, and if it didn't go well, then this is extra practice to kind of help you with it. It's the same idea, except instead of a 3D shape, you just draw a 2D path. Ampere shape. There will be amps involved. Alright, so what generates electric fields and what experiences a force due to electric fields? Remember I told you we're going to use the same logical sequence.
With electric fields?
Yeah, electric fields. Let's see if you all remember. What generates electric fields and what experiences a force due to electric fields? Is it mass, moving charge, stationary charge, or everything? Think back to when we covered it. Pick the one that you're familiar with. All right, 10 more seconds. All right, in 5, 4, 3, 2, 1. All right, what makes electric fields experience a force? Let's remember our equation for it. Let's write the equations. Okay, Q1, Q2 over R squared. What makes a field? KQ over R squared. So what makes a field something with charge? For electric field, it's squared. For voltage, it's over R. So it's something to do with charge. Now, I'll be generous and I'll lump moving charges in here, but really stationary charges are what I was looking at. We never did any moving charges when we talked about electric fields. But I will be generous and I'll just highlight the word charge here and I'll give the answer for it. Everything does not make an electric field. Now, everything is made of electrons. Everything is made of protons. But what if you have equal numbers of both? They cancel out. There is no field. And there's neutrons. Neutrons have no charge. If I got a big old lump of neutrons, that has no charge. So, this is a reminder to you all, the reason for this question originally was just the things that make a field experience a field. What makes an electric field? Charges. What makes a gravitational field? Mass. The things that make a field experience a force due to said field. That was the whole point of this question, but I guess it's a good review on this as well, on the concept of it. So what generates magnetic fields? Hint, it's the thing that experiences a force due to magnetic fields. Is it moving charges, mass, stationary charges, or moving objects with mass? So from this last week, what were the things experiencing a force due to a magnetic field? Because those are going to be the things that make the fields. All right, give you all 20 more seconds. All right, in 5, 4, 3, 2, 1. All right, so let's write the equation. What experiences a force due to the magnetic fields? Q, V, B, sine theta. So what experiences a force due to a magnetic field? Moving charges. This is what delimitates them from electric fields. Electric fields are stationary charges. Moving is magnetic force.
I know this is probably a little extreme, but like, what if a charge is like physically not moving but just spinning?
Yeah, that's actually a very, very good question. That's very complicated. So he asked, what if the charge isn't moving but it's spinning? So you actually touched on a piece of quantum mechanics there. There is a characteristic of electrons that we call spin, and we pretend like they are spinning, and it does result in them making a magnetic field. But that's quantum mechanics. And are they physically spinning? We call it spin, but it's not really clear. Yeah, it's a really good question. These are the kind of questions that make people discover things. All right, so nice summary. Oh,
So that Q, like in the F equals Q V times D sine theta.
yep,
Like the Q is that.
that's charge.
It's a moving charge.
It's charge. If by velocity is 0, though, there is no force. It needs to be moving.
Also, the velocity makes it moving.
Yeah?
Q times V is moving.
If V is 0, then it's just a stationary charge and there is no force. Yep. Yep. All right. This is a quick summary of fields and forces. What makes gravitational forces? Mass. What makes gravitational fields? Mass. What makes electric fields? Charge. What experiences electric fields? Charge. What makes magnetic fields? Moving charges. What makes it experience the force? Moving charges. The things that make a field experience a force due to said field. That's the connection I'm trying to make here. That's the logic with fields. What experiences a force, therefore generates the force. Generates the field that will affect another one. All right, we got a new right-hand rule. This is, there's another one here, and I'm going to try to teach it in a couple ways. So, how do we find the direction of this field? The rule is, this field makes a circle around the wire. Every current-carrying wire, every moving charge, the field it makes around it is a circle. We can see that in this picture here. So there's a bunch of circles around it. How do we determine the direction of this circle? You point your thumb in the direction of current, and your fingers make that circle. Now, if you want to find the field at a specific point on said circle, so I'm just going to pick some random spots on this circle. Say I want to find the field to the left of the wire. You find the tangent line to that circle. This is ultimately any process I teach you, this is what you're doing. So this is the field at a bunch of random spots. If I want the field in front of it, then it's any of these arrows. You pick where you want the field, you imagine that circle, and you draw the tangent line to said circle. These circles are just a bunch of tangent lines strung together, and they should be getting weaker as they get farther away, not stronger. So we'll draw them, as you get farther and farther away from this, they should get weaker. So I guess I'll just draw it technically correct. But we don't really care too much about that. The strength of it right now. All right. Any point here on the back, same thing. They're going to be pointing tangent to the circle. This is one way of doing it. The other way, I'll teach you all, and then we're going to practice this, is you point your thumb in the direction of current, you point your fingers to where you want to find the field, and your palm gives you the direction of the field. So this is the second way. This is option 1. I'm going to make option 2 real quick. Right-hand rule 2, option 2. Point thumb in the direction of current with hand flat. Point fingers towards where you want to find field. Keep hand flat entire time. And then last, your palm points in direction of the field. They do the same thing. Either way, pick your favorite. So, I like the circle one because the circle one is gives you a better conceptual understanding of what the field looks like everywhere. If you imagine this circle, that's what I kind of do when I do these problems. I imagine this circle and I imagine the tangent line to that. That requires a good amount of visualization though. Alternatively, if you want the field over here at this point, thumb in the direction of current, point my fingers to the point on the left, palm points in the direction of the field. If I want the direction of the field kind of in front of the wire, thumb in the direction of current, point the fingers towards that, palm in the direction of the field, where it's upright. Yeah.
Are those rings on the circle example?
Those are magnetic field. That's what the magnetic field looks like around it, everywhere around it.
Is that kind of could you almost relate that to the energy levels that electrons spin on in atoms?
If we think of electrons orbiting in a circle, even that's not actually true. They don't actually make circles. Yeah, so that gets more complicated. All right, so we're gonna do these couple examples together, and then we're gonna try it ourselves. We're gonna try a clicker question. So I'll do a couple with you. So this one, you point your thumb in the direction of current, and then imagine a circle going around this, orbiting this thing. I'm gonna do it both ways. If you imagine a circle kind of orbiting this wire, that circle is going to be making this, I don't even know what direction you call that, clockwise or counterclockwise, depends on what side of my hand I stand on. It is a circle that kind of goes out of B. We can see here that circle, you imagine your hands rotating around. On the bottom, it's going to point out. So the magnetic field at point B is going to point out of the page, and at the top, it's going to point in, and it's kind of making this circle looping around the thing. Okay? If you want to use the other technique, the option 2, put your finger in the direction of current, point your fingers to the point, and your palm points out of the page. You get the exact same answer. If you want the top one, thumb in the direction of current, fingers towards the point, my palm points into the page. Make sure you use your right hand. If you use your left hand, you get the wrong answer.
You should have bottom hand.
Yeah, thumb in the direction, hand points upward. All right, the one on the right side. Again, we're going to start with the circle example. We point our thumb down, and that gives us a circle that kind of goes out of D and into C. The circle is kind of orbiting it. So at point D, that circle would point out. And then at point C, it's going to point in. If you want to use option 2, put your finger down. Point it towards D, and my palm points out of the page. Great, you get the exact same answer. You want the other side? Thumb down, point your fingers towards it, your palm points inward. You get the same answer. Both work. I emphasize the circle one because if you can imagine the whole field, that's just a bit more rich in terms of content, but they both accomplish the same thing. I'm never going to ask you to draw the entire field. I'm always going to ask you to find the field at this spot. All right, great. See if you can do it. So I've given you all a current carrying wire, and I drew a flat plane that intersects it so we can actually get kind of the answer here. So I got a wire going straight up, and I have a point that's kind of quote unquote out of the board, kind of more towards you all. Is that point, it's a point in front of the wire? Is the magnetic field that point towards the wire, away from the wire, left or right? Yeah, point B, so this is like a flat piece of paper like this. Yeah. Really hard to draw three-dimensional. Yeah, so this is some point in front of it. All right, give you all about 20 more seconds. All right, in 5, 4, 3, 2, 1. So we're going to do both techniques. All right, so I'm going to do the circle technique first. I put my thumb up, and the current makes a circle. Based on how I'm looking at it slightly from above, so that circle is going to kind of go counterclockwise. So if I want the field at this point, it's to the right. It's tangent to that circle. At that exact point, that circle is going to the right. Great. That's one way. The other way, put your finger up, your thumb up, point your finger at the point which is in front of it, your palm also points to the right. There you go. There you go. Thumb up, points out of it, palm points to the right. Because the point I want is in front of it. Yep. So yeah, if you want the field back here, it points to the left. But we want this one. I didn't ask for the field everywhere. I asked for it at one specific point. I can't ask for it everywhere because then there's an infinite number of answers. So, great. To the right. Now, we can think of these current carrying wires in the same way we think of point charges. Specifically, if I had a bunch of current carrying wires and I wanted the net field, I would just find the field into each one and then add them all together. Just, keep that in mind for the future. Our current carrying wire is kind of like our unit here. Each wire is going to make a magnetic field. If you got a bunch of wires, just add up all the fields. We'll see that later. All right, so now I'm going to give you a law, and I'm not going to derive this law because it's very mathy, and actually I don't even know the full, it's a law. It's an observation of reality. It is observed from doing experiments and things like that. So honestly, is it really a derivation? Not really. It's going to look gross. It's going to have an integral. You won't actually have to do the integral. The law I'm about to show you is purely going to be used to derive two equations. You will not actually need the equation that I'm about to show you. Okay? By Savart law, you will never actually use it to solve the magnetic field due to a thing. I am going to use it in front of you to solve a couple scenarios, and what I get from that we will use. Okay? So, by Savart law, mu naught over 4 pi times I dl sine theta over r squared. It's a cross product on top. Again, you will not need to actually do this integral. Let me make that very clear. You will never be using this integral to determine the magnetic field. In class, we are going to use it to derive the magnetic field due to a straight wire and due to an arc of wire, and then we'll use those equations moving forward. Okay? So, it's not worth spending the time and energy to, because this is only used for two scenarios. We only use this for two scenarios, and the solutions from those are what they are. There's not much benefit to deriving it. Deriving yourself is good as a physics major, things like that. If you really want to practice integrals, feel free. But great. Okay, so let's do it for an arc of wire. And I'm going to kind of go through this very quickly for the reason that, again, you don't need to know this. All right, here's an arc of wire. We're going to use Biot-Savart's law. So we're going to write the law. It said that the integral of mu naught over 4 pi times dl times r times sine of theta all over, there's no r on top, don't know why I put that, dl times I sine theta. All right, this one's going to be really easy for us to solve, believe it or not. Mu naught over 4 pi, it's a constant, gets pulled out. I, that's a constant, that gets pulled out. We're finding the magnetic field due to this wire. So, mu naught I over 4 pi integral. We're going to do the same trick we've been doing every single time we have an arc of wire. We're going to change dl to r d theta. Every single time we've done this, we've done this a bunch of times now. dl equals r d theta. R d theta sine of theta over r squared. You know what's really convenient? R is also a constant. R is the distance from the wire to the point I'm trying to find the field. Everywhere on this wire, every little dl that you can draw is going to be the same distance. One of these r's even cancels for us. So we get mu naught I over 4 pi times,
Where's the R?
thank you, right there. Sine of theta. Theta here is the angle between, let's go back to this so we can see it here, the direction of current in R. So this is the angle between this cross product here. If we look at this picture, I, R, and DL are always perpendicular to each other. If you need a proof of that, just pick another point. Here's the direction of DL. There's the direction of R. They're perpendicular. You want another one? There's another one. Still perpendicular. So what does this angle end up being? This ends up being 90. Sine of 90 is 1. Super easy integral. What's the integral of d theta? It's just theta. So, boom, there's the equation. You got an arc of wire and you want to find the magnetic field from it? Mu naught I theta over 4 pi r. You do not need to know how to do this derivation. You do need to know how to apply this equation. So it's all, written there, typed up in a beautiful typed way. There's the equation.
Oh, radians now?
Yes, it needs to be, anytime you want to plug angle, anytime you want theta by itself, not in a sine, not in a cosine, not in a tangent, you need to use radians. Radians are real. Radians came from that r d theta. You need to use radians here. If you use degrees, it will be wrong. Degrees are made up. Why are there 360 degrees in a circle? Because some human decided. Why are there 2 pi radians in a circle? Because if you take a string and you wrap it around a circle, the ratio between the circumference and the radius is 2 pi r. That's a physical rule of the universe, not decided by a human. It's the ratio. Radians is determined by the ratio of the circumference to the radius. It's math. Yeah.
What's the difference between mu naught and epsilon naught?
Yeah, great question. Mu naught is 4 pi times 10 to the minus 11. I kind of skidded right past that. The value of mu naught is 4 pi times 10 to the minus 7. You all just have to know that, it's going to be a given on the formula sheet. But it is it's a constant. It's called the permeability of free space. Epsilon naught is called the permeativity of free space. And 1 is for magnetic fields, permeability is for magnetic fields, it's at mu naught, epsilon naught is for electric fields. You can think of it how easy or difficult it is to make, in the case of epsilon and electric field, how easy or difficult it is to make a magnetic field. Different materials get different ones. Get different, these values, which we're not going to get into in this class too much.
Is mu naught only used in this equation?
Mu naught will be used in every equation used to find the magnetic field.
Okay.
Yeah, because of Biot-Savart's law, it shows up in the law. It's a proportionality constant. Something that's kind of nice from mu naught is you notice it cancels out with the 4 pi on the bottom here, whatever that's worth. Yeah, it cancels out with this 4 pi here. Why then is it this way? Why didn't they just combine into one constant? I honestly don't know the reason. Usually we do combine constants into one value, but for this, they decided not to. Okay, I kind of do know why. I have to fact check this. I forget which ones when you divide. When you divide one by the other, you get the speed of light. Yeah, I think it's mu naught over epsilon naught based on just the numbers I'm seeing here. All right. Great. Try it. I'll even put the equation for you here. Mu naught I times theta over 4 pi r. What's the magnitude of the magnetic field at the center of a half circle of wire with radius r? Now you're kind of lucky that I didn't put any answers here in degrees. But I'm just going to pick a random one. Let's put 90. Let's see here. Let's make this one 180. Great. Did the fact that I put those mean they're the right answer? I'm going to let you think about that for yourself. I'm not trying to trick you. Well, I'm trying to see you're paying attention. Not to me typing stuff right now, but to the equation. Pretend like those are always there. See if they make sense or not. If they don't make sense, don't think it. But write out this equation, and you only need to plug one thing into it. In this current, this wire has a current of I. This circle has a radius of R. So you only need to plug one variable in. So we'll do this question and then the next one, and that'll be our it for today's class. So we'll have one more after this. Give y'all 10 more or 20 more seconds on this one. All right, in 5, 4, 3, 2, 1. All right, so we just plug in the numbers. This thing has a current I, it has a radius R, so everything stays the same. Mu naught I over 4 pi R. The only thing you need to plug in is the angle. What is the angle for a half loop? Pi. Pi's cancel. Not that one. There it is. Why did I put this 90 in the 180? To see if you were trying to put degrees in and trying to force it. They don't even have an R in the bottom. They're double wrong. All right, great. Next problem. Told you, one more. What is the direction? Hint, pick a couple pieces on this wire. You might need to pick more than one piece because it's a curved wire. So pick a few pieces. Find the magnetic field at each piece. And then add them together at that point. All right, 20 seconds. All right, in 5, 4, 3, 2, 1. All right, I'm going to use option 2 for the sake of time, and it's quicker. Point your finger in the direction of current. Finger towards the point, your palm points in the direction of the field. Look what happens when I spin my hand around. Wow, it always points in the same direction. They all point out of the page. They all add up. They all make a bunch of circles where they all intersect there and point up. Have a good one, y'all. Next class, we'll do a straight wire.